Hello there, Atheist Junior here, your friend and humble narrator. And today I'm joined by friend of the channel, Grayson.
Hey.
And also we have Adam Lohr here, who's a fellow atheist, but he is somebody who disagrees with me and Grayson on Big Bang cosmology. So he doesn't accept the Big Bang theory as being true. He also doesn't think that, I believe he doesn't think, he does think the universe is eternal, or what was the second part of it? Or just, why don't you explain your position real quick rather than me explaining it for you, Adam? And how are you doing this evening? Thanks for coming on the channel.
Yeah, I'm doing all right. Thanks for having me, guys.
Sure.
Yeah, I believe that the universe is past eternal. It's always existed. I don't believe in creation. I don't believe in expansion.
Yeah.
It's like Grayson and I earlier were making the distinction between steady state and past eternal, where steady state is like, it's like expansion and creation, but it's like past eternal. But I'm not a steady state believer.
So basically, if I'm understanding this correctly, like you believe that the universe existed indefinitely into the past, but you don't agree that space-time is expanding or has expanded, like space-time has been in a static state. Correct?
Yeah, I don't believe that redshift of galaxies is velocity. I don't believe that there's a metric of space-time that's expanding. I don't believe that space or time is expanding. I just think that it's static. It's not, the universe is not changing size.
But we can observe this expansion through telescopes, though. Or do you disagree with that, or are you just saying that?
Yeah, we definitely don't observe expansion. We observe clustering of galaxies. They're not moving apart. They're clustering together.
What is that? What do you mean clustering?
Like galaxy clusters and superclusters. They're not, the galaxies are not moving apart as the Big Bang says. They're clustering together. They've clumped together. They're not moving apart.
Grayson, I'm going to let you go ahead and just take over.
Yeah,
for a second.
I'm very interested in how you arrived at this view, because I assume at one point in time you would have accepted the scientific consensus on this, and at some point something happened to make you question and eventually form this belief that's contradictory to that. So
Right.
Before we kind of get into the nitty-gritty of the evidence and the details, and I do want to get into that, but at first I'm just very curious about how your worldview kind of came about.
Yeah, so I am very interested in science. I have a lot of books and stuff, watch a lot of videos and stuff on science. I spent a lot of time and money and resources into studying the Big Bang Theory, which I used to believe in. And that's like something I'm very interested in. And the more I was reading about it, the more I found issues with it. So it's not like I'm just coming at this from like being against it. I actually like am finding out issues with relativity and issues with things that I'm excited about and like promoting. And it's like, oh shit, I find out that it has all these weird problems.
So that to me, that requires a certain confidence that what you're finding are actual issues or inconsistencies with the theory, rather than just like you misunderstanding something. How do you draw that distinction between, maybe you're not understanding a certain concept in physics versus that concept actually being like, problematic or inconsistent?
Like
how
reading
do you
science papers, for example, like like I bought into the idea that the cosmic microwave background radiation temperatures were evidence for the Big Bang Theory. But when you look into it, the temperatures predicted by the Big Bang theorists were way higher than the temperatures predicted before the Big Bang Theory. And there's a weird, very wide scale of all these different numbers that are all completely wrong. There's like a bunch of stuff like that. It's like, at first, a lot of stuff seems really convincing. And then when you look deeper into it, there was stuff before that was way more accurate and it was right. And then the Big Bang Theory keeps failing all these tests.
So then why do you think that? Because I mean, the majoritarian position of physicists in the 20s and 30s was like a static universe. And like, that's what the consensus was. So then why do you think that the evidence was enough to change the consensus of physicists?
Penzias and Wilson.
What was that?
Like Penzias and Wilson. You know those two guys, right?
Yeah, care to elaborate?
You know
Like
who
you're
Penzias
talking about the
Wilson is?
discovery of the CMB in the 1960s, right?
Well, that's what people say. You guys, you've been saying discovery about this. It's not a discovery, but yeah, that became this big news item, and that convinced a lot of people. But when you look into the history of it, the background radiation was known about in the 1800s before the Big Bang Theory. The temperature was figured out before the Big Bang Theory.
You understand how that would be a contradiction to what you said earlier about how the predictions for the temperature were totally wrong until it was observed, and now you're saying
for
that
your
the
guys' theory
already known.
No, see, because you're assuming that a background temperature has to be a Big Bang background. That the background temperature was already something that the static models had, the eternal universe had. But so another issue is Penzias and Wilson won the Nobel Prize for making those measurements, and then they thanked the guy that had already discovered it in their acceptance speech in the 40s, like things like that. It's like they didn't really discover it. They weren't the first ones.
So what? I mean, science, we stand on the shoulders of giants. Like, science is a collaborative process. I mean,
I also have to clarify here that like
are you guys grilling me on what I believe, or are we
like
talking
you're
about
talking about the theoretical like models that they were using to, but like that was theoretical. Like the actual discovery of the cosmic microwave background was by those two scientists that won the Nobel Prize.
it wasn't discovered? That's not a discovery, though.
yes, it was. I mean,
Yes,
what?
it is.
Yeah, I don't know what else you would call it. And I don't
They
think me
already
and
knew
Grayson are
what.
trying to grill you. I mean, we're having a
Yeah, so really, we
discussion.
agreed to talk about the cosmic microwave background radiation temperatures in the Big Bang, but you guys are grilling me on this. That's fine. But so yeah, it is actually true that Penzias and Wilson did not discover the CMB. They didn't.
You're saying they didn't discover it because it was already discovered. It was already known about.
Yeah, the microwave background radiation was known about in the 1800s, and it was already measured in the 1940s. Wilson thanks McKellar and Adams in his acceptance speech. He says, "Thank you to these guys that already measured this shit." Like,
So it's true that they knew about the noise, the noise, like a static in a radio. But what the Penzias and Wilson did was they showed what the significance of it was, and they showed what it actually was. So they were able to detect this. But what these guys did is they showed what it actually meant, and they showed how important this was in terms of predicting the evolution of the early universe. And I don't see why it invalidates what they did just because it was previously, like, Einstein gave us, theories of relativity, but gravity was already, you had Newtonian mechanics, which is a lot simpler, but it was built upon that, and both of them can coexist. It doesn't invalidate what Einstein did just because Newton had already had theories of gravity already.
Right. So if the background temperature of the universe is known in the 1800s by people who believe in a static universe that's eternal, and they accurately predict the temperature of that in like the 1800s and from the 1800s to the 20s, and the Big Bang people say it's going to be 50 Kelvin, it's going to be 100 Kelvin, it's going to be 23 Kelvin, and they're saying it's going to be 2.7 Kelvin. They measure it and it is 2.7. How do you not see that as a contradiction of the Big Bang Theory?
Okay, so I think I know what you're talking about, where they predicted a like background temperature as a result of like scattered light, right? But the issue is, and the reason why that this was moved away from towards the CMB being a result of the Big Bang is because like frequency observation showed that it forms like a black body spectrum, which is something that like a static universe, if this was just scattered starlight, would be unable to account for in the model, but the Big Bang does.
Okay, so that's not true. But this is why I want to focus on CMB temperatures, because you guys don't want to stick to that topic because you know that it's like
That's
you
what I
asked
was
me
talking
first.
about.
You guys asked me why I believe what I believe, and you didn't let me answer. And then when I'm giving evidence against the Big Bang Theory, you don't want to talk about it.
But I just directly addressed it. What I was just brought up was talking about CMB, like thermal measurements.
You're
Yeah.
changing it from the temperature to a black body, which you're claiming the other
Black body
theorists
is
did not.
temperature.
Those are directly related to each other. He's not.
But you're
changing
claiming
the
that the other theorists did not believe it was a black body, but that isn't true. And we haven't even talked about who the other theorists are. Like the temperatures predicted by the Big Bang by Dickey and Gamow and all those, Alpher and Herman, they were a wide range of temperatures. And in their papers, they said we should expect it to be higher than what the other people are saying. There was already a concept of a background temperature. They already knew it was 2.7, 2.8 or something like that. The theory, I mean, they already had predicted by calculation that it would be. The Big Bang Theory, the proposal was that there's additional heat in addition to that. And that was found to be false. So that is a falsification of those predictions. Those predictions are inaccurate. And those are the old versions of Big Bang Theory. You know that today it's not the same old-fashioned Big Bang Theory. They have dark matter, dark energy, inflation, Kerphoton field, all that stuff.
So what about the Soviets who predicted the cosmic microwave background in the correct temperature range like a few months before those two scientists in the 60s found it?
What about it? That's like in the 1960s. Why not look at the information that was known in the late 1800s? They already knew this in the late 1800s. Like,
no,
who cares about the 60s?
They didn't. And again, I feel like this is fallacious to say that because there were people earlier who maybe knew about some elements of the CMB, about the Big Bang, about temperature, that somehow invalidates what the Nobel Prize winners did. It doesn't. Like, science is a collaborative process. If these people made a prediction about the temperature, like Alpher and Herman, they started estimating that it would be 5 Kelvin, and then like later they said it was going to be 28 Kelvin, but that was because they misestimated the Hubble constant, and then they went back to their original prediction, what was really close to the actual temperature, which was like 2 point something Kelvin, which is a really accurate prediction. Yes, it is.
It is.
It's
that's
within
a within
a few Kelvin.
But that's the people who didn't believe in a Big Bang Theory already had calculated it to be 2.7, 2.8. They calculated it precisely. What do you mean you don't think so? That's what I'm saying. Let's look at the numbers. Let's look at the predictions.
Yeah, so
that's what I wanted to talk to you about, AJ. That's what we talked about months ago.
I'm not familiar with it.
I've been trying to talk to you on Twitter about it. I've left you comments. You've been avoiding my comments. You've been.
I've been avoiding your comments.
Okay, calm down. I'm aware of what you're saying, right? The McKellen guy, right? This was, I don't think the 1800s, but sure. McKellen made a prediction about the background temperature being around 2 point something Kelvin as a result of like the entire universe rotating, right?
You're mixing like 3 different things together.
Okay, well, then so who's the guy in the 1800s that observed? I don't know, man.
There's multiple people. Like, it's not just one guy. There's multiple people.
Okay, and so you're saying...
So that's what I want to talk... That's what I'm saying. That's what I want to talk about. I want to go through and talk about these temperature predictions and the accurate ones from the non-Big Bang people, and then every single one that's from Big Bang is completely inaccurate.
What about the prediction of like adiabatic transfers in the cosmic microwave background that was made by the inflation hypothesis that was then like observed to be true? I mean, I don't think any of the steady state or static prediction models ever talked about any adiabatic processes.
So you're skipping ahead to the end of the 20th century.
Well, we live in the 21st century, so we should be talking about the evidence that is available today, not just like stuff from the 1800s and the 20s.
Let's decide on what you guys want to actually discuss and focus on that, because it's all over the place. This is why I said I want to focus on CMB temperatures. And that's what we had agreed to with it. Well, that's what AJ and I had agreed to.
That's what we've been talking about this whole time.
No, because I'm talking about CMB temperatures predictions by the Big Bang theorists.
Yes, that's what we're talking about.
Evidence.
I just named one. Like,
You
you
know,
a diabatic means a transfer without heat transfer. So it's like a transfer of work that doesn't involve a transfer of heat. That was a prediction made by the inflation model that we then looked at, like the cosmic microwave background, and we saw evidence of adiabatic processes and that matched the prediction. Now I'm talking about a direct prediction from the inflation model of the temperature phenomenon in the cosmic microwave background. This is totally on topic.
Inflation was made up in the 80s by Alan Guth. That's after the CMB was already measured. So that's not predicting a temperature.
No, it is because we didn't have accurate observations of the CMB until the 90s with like the Planck and the WMAP and all of these different fine scale telescopes.
Right, and then they found the horizon problem, the flatness problem. They found all these
problems. Who's changing the subject? You wanted to talk about the CMB temperatures. I brought up a specific prediction about CMB Grayson. Temperatures that was verified in the 90s.
I'm not talking about inflationary Alan Guth shit. I'm talking about the original Big Bang theorists that made those predictions that were then, you guys are counting as a verification of the theory when it was measured in the 60s. That's what I'm talking about. I'm talking about the temperature predictions from like the 40s and stuff.
Okay, I just wanted to say really quickly that this guy in the 1800s who predicted he predicted the radiation of Charles I don't know how to say his last name. Charles Guillermo estimated the radiation of the stars to be 5 or 6 Kelvin, but that was a thermal non-microwave background temperature prediction. So that's not even talking about the CMB. That's a different thing.
Right, so right. And that is that the temperature of the stars is not the same as that was before
that's what I'm saying.
Even what a galaxy was.
Yeah, that's what I'm saying. So I don't know why you're trying to say, I guess, that the Nobel Prize winners, that like their discovery was not a discovery, that it was invalidated because this person had made a prediction in the 1800s.
So in the 1940s, Adams and McKellar measured the CMB using cyanogen molecules. They already knew what it was, and the Big Bang theorists knew what it was. And Penzias and Wilson already knew about that and thanked them in their acceptance speech. What Penzias and Wilson did was they used radio astronomy to measure it, which hadn't been done with radio astronomy, but it had already been measured in the 1940s by Adams and McKellar using other methods. And they were aware of that. It can't be a discovery if he thanks the guy that already discovered it in the 40s for his discovery.
What is the implication, though? Like, so what? Well, you're saying that
I am curious about where you think that the cosmic microwave background is coming from.
What is okay? So you're saying it is a discovery, and I should point for the third time why it's not a discovery. Do you accept that that's not a discovery if what I'm saying is true?
Just no. I mean,
like, have you heard of Adams and McKellar?
Not invalidated just because earlier people, made cracks at this, and earlier people, it's like, today we have Charles Darwin discovered natural selection, but today we have some evolution is called the modern synthesis because Darwin didn't even know about genetics. So now we have genetics, we have evo-devo biology and epigenetics and all these different things that are added onto it. But it's not invalidated just because Darwin discovered natural selection. Science is a collaborative process. So I think it is still an important discovery, and that's why they won the Nobel Prize for it.
But there's a difference between measuring the CMB using radio astronomy and discovering it. They didn't discover it.
Can you explain how it is that they measured the CMB? Because what I'm coming across is that they were measuring like stars. Like how are they measuring the CMB?
Penzias and Wilson measured it using radio astronomy.
No, not Penzias and Wilson. I'm talking about Adams and McKellar, like the ones in the 40s that you were talking about. Because what I'm seeing here is that it says that they measured like observations of absorption lines in the spectrum of stars.
Okay, AJ, are you familiar with Adams and McKellar? Have you heard of that before?
No.
Grayson, are you familiar with Adams and McKellar? Have you heard of Adams and McKellar before?
No, not before this.
Okay, so Adams and McKellar measured the CMB in a different way. They use cyanogen molecules, and I don't even understand what the fuck they're doing, but Wilson thanks them in his acceptance speech. So Adams and McKellar are the first ones to measure the CMB.
And so what?
So the name of this paper, they say that what they said that they were measuring is molecular lines from the lowest states of diatomic molecules, like the cyanides that you're talking about, probably present in interstellar space. So what they were saying, what they thought that they were measuring is the rotational temperature of interstellar molecules. So they thought that there were just some molecules floating around in space that had a rotational temperature, and that's what they thought that they were measuring.
Right. Well, I mean, if you want to be a Google scholar and go by that, that's fine. But if you actually look into the history of it, it's significant. That's what I'm pointing this out, is that Penzias and Wilson weren't the first to measure it. It was already measured in the 40s. So any predictions after that is not a prediction. It was already measured by Adams and McKellar. It was already known. So if one of these Big Bang theorists makes a quote unquote prediction after that measurement, it's not a prediction if you're saying it's the same thing. What they predicted was there was going to be a temperature that was found that was higher than what Adams and McKellar measured. They thought that there was an additional temperature. When they made more and more accurate measurements, they found that there isn't some additional background, like leftover heat from the Big Bang. It's just the same temperature that people expected in the 1800s that was already measured in the 40s.
And so what do you think this is coming from? Where is this heat coming from?
What do I think? Doesn't matter what I think. Like, in terms of talking about what's wrong with the Big Bang Theory, it doesn't matter what I think it is.
Why not?
Because it doesn't have any effect on the fact that it's a wrong theory that's been proven wrong. And they had to make a new one.
You say that, but you understand that that's a very contrarian opinion, and you kind of have to have some strong evidence to support that it's been disproven if, like, all the experts in this field would disagree with you.
That's an argument from authority, which you love. But you're like, if you guys, okay, Adams and McKellar measured the CMB. Any prediction made about CMB after that for anyone that knew about Adams and McKellar couldn't have been a prediction. Do you agree with that?
No.
Okay, go ahead. Actually, in a sense, it was a prediction because they were predicting an additional temperature to it. They were predicting
what
they were something hotter than that.
Like, what they said that they were measuring was not a cosmic microwave background, right? If you had read their paper in like the 50s, like, and you were trying to make predictions about a cosmic microwave background, like, I don't see why the one would influence the other, because where you're coming from is I don't know, man. It doesn't. I don't see how that follows, because like what they're using to predict the cosmic microwave background is like the mathematics of the Big Bang model, and that's what happened when the Soviet scientists published their paper in 1964. I mean, they weren't using Adams and McKellar's data.
I don't know which Soviet scientists you're talking about.
So there is direct. I hate to change the topic, but perhaps we should move on. So there's direct evidence of cosmic expansion, Adam. How do you explain that, or how do you deny that? Because
okay. What do you mean by direct evidence? Like, you can watch it happen?
We can we can use telescopes, and we can observe the redshift of galaxies, and we can see that not only are galaxies as well as space-time itself, the galaxies are moving away in every direction. And not only are they moving away, the speed of expansion is increasing because the light from those galaxies is redshifted.
Okay, so you are interpreting the redshift as what velocity metric expansion of space. Which version are you interpreting that as? I'm assuming the lambda CDM model, right?
Yeah, as a metric expansion of space-time.
Okay. So that was made up in the 80s, right?
It wasn't made up.
Alan Guth didn't make up inflation?
No, you're saying it's made up is implying that it's fake or it's bullshit, so I'm not going to grant that.
Okay, so well, it is fake and it is bullshit and it does require supernaturals. It requires dark matter and dark energy and these
That's not
fantastical.
supernatural.
Alan Guth didn't discover it. Edwin Hubble was the one who discovered
Talking about inflation,
redshift.
Not redshift.
Yeah.
Well, we were not talking about inflation, I believe. Like the subject was redshift. You were the one that brought up inflation in response to.
Well, you guys are talking about
I did. I brought up cosmic expansion. And I said that the evidence for that is the fact that the light from galaxies is redshifted.
But AJ, okay, yes, let's address redshift. But there's a difference between expansion, which is the classical version of the Big Bang, and inflation, which was a new version made up by Alan Guth. I don't know what you guys want me to call it. It's not a what should I say?
That's fair enough. It doesn't matter.
It does. I mean, it does. Okay, it doesn't matter what I call it. Okay, so yeah, redshift. So you guys are. So that's what I'm asking. Are you interpreting redshift as velocity or as metric expansion?
Metric expansion. I already said.
I'm asking AJ.
I don't understand the question.
Right. So in the olden
okay,
days,
AJ, he's asking whether or not you think that galaxies are physically traveling at a velocity, or whether or not the space in between us is expanding.
Yeah.
The space in between is expanding.
Okay, because the earlier versions were that it was literally a velocity, right? It was a Doppler effect.
Okay,
so
well, in science, sometimes we get things wrong, and then later on we discover the truth. That's part of science.
Right. Well, I mean, if you believe that space can expand in principle, that's different. I don't think that that's even possible. But what are you even talking about? So you're saying redshift is evidence of galaxies moving apart, but it's not the galaxies moving apart, it's space moving apart, right? That's what.
Hold on a second, Adam. So just to prove that the expansion of space-time is possible, how do you interpret the 1998 observations? Right, these were two separate independent teams that both observed in 1998 that the expansion rate of space and time is accelerating. They did that through direct observations.
They're comparing different things. They're looking at galaxies and they're looking at quasars. They're comparing different types of things.
No, they weren't looking at any of those things. For the 1998 measurement that the expansion rate is accelerating, they were looking at supernova, both teams.
Right. That's what I'm saying. So if you look at the redshift of galaxies and you look at the redshift of quasars, you look at supernova, there's different things you can look at and get different results because it's not a matter of the universe actually expanding.
So then why did two independent teams get the same results in 1998 that the rate of expansion is accelerating? I mean, they were independent teams getting the same result.
That's an interpretation of evidence, though. That's not, they didn't measure expansion. You can't measure expansion. You can indirectly infer it.
Grayson, do you have a link for that?
They're inferring it. You think that they're measuring actual expansion?
Yes.
Besides outside of looking at redshifts, you think that there's actually going out and making measurements of how much stuff is expanding?
They're making measurements of the redshifts of supernovas to compare how redshift it is since it went supernova, and that is how you can tell that the rate of the expansion is increasing. And AJ, if you search like accelerating expansion of the universe, you should be able to find the two teams were like. I think like the supernova project, and I don't remember off the top of my head, but in 1998, the two independent teams both measured the rate of the expansion of the universe as accelerating.
Okay, I'm going to put that link in the YouTube chat if anybody wants to.
Okay, so you guys believe that that's because of dark energy? Is that correct?
I mean, that's
dark energy is just a stand-in term for.
Yeah, that's currently the hypothesis.
Yeah.
Okay. So according to the lambda CDM model, which is the concordance model, the standard version of Big Bang today, according to that theory that you guys are supporting today, right? according to that model, what you just described is because of dark energy, correct?
That is the hypothetical explanation.
Okay, so maybe it was, maybe it wasn't. I mean, it's part of the name of the theory now, the lambda in there, right?
It's a very broad theory covering most of our current understanding of cosmology.
Yeah, so
Okay.
dark energy is just the name that's given to whatever force it is that's causing the rate of expansion of the universe to increase. So we don't know what's causing that. Dark energy is just a sort of stand-in term that we use until, if ever,
Right.
scientists discover what that phenomenon is. So
it's completely unknown. How much of the percentage of the universe does dark energy make up?
do you mean dark matter?
No, he means dark energy. It's around 71%. The last estimate I saw.
71%. Wow. Okay, and how much is dark matter?
Like 21%. These are just the numbers that I'm remembering off the top of my head, but those
What's
are just
the observational evidence for either of those, and any kind of scientific theory that they can even be possible according to the laws of physics?
Yes, it's called the lambda CDM model.
The lambda CDM model is a particle theory of how dark matter works?
No, obviously not.
That's what I'm saying.
That's
is
not
it
what you
defies the
asked.
laws of particle physics.
Yeah, that's not what you asked. You didn't ask anything about particle physics.
So is it something that's completely unknown, or is there a theory of physics that describes how this stuff works?
It is unknown, and it is in part of the lambda CDM model. We don't know the constituents of dark matter or dark energy. We don't know what it is on like a particle physics level, but we can observe like the effects that these things have on our universe.
Right, but in the lambda CDM model, like actually even outside of it, the idea is that there's this special energy and special matter that's non-baryonic, isn't it? It's not ordinary matter. It's some new exotic form that cannot be measured, cannot be tested in a laboratory. It's completely hypothetical.
No, wait, hold on. It can be measured. Okay, that's a falsehood. It just doesn't interact with the electromagnetic spectrum. It does interact with gravity and the weak force, or hypothetically the weak force, but definitely gravity.
Well, matter does. So there's no way to show that that's non-baryonic matter, though. Like, in other words, I would guess that it's probably matter, not imaginary, exotic, fantastical, supernatural matter that doesn't exist that you guys made up.
Well, all matter that we know of that's not dark matter interacts with the electromagnetic force, but this matter that we observe having gravitational effects does not interact with the electromagnetic force.
It's never been observed. It's made up.
We would definitely see if it was regular matter.
You think that dark matter has been observed?
Yes, its gravitational effects have been observed.
No. You're starting with an assumption and counting it as evidence for the assumption. There's evidence of gravitational effects, but that is, and then you're saying that the question mark that
those can't be explained by our current understanding of gravity.
I'm saying non-baryonic matter has not been observed.
Okay, so you're making a weird thing about observation here, because it sounds like when you say observation, you're talking about interactions with the electromagnetic force. Like, what kind of observations outside of the electromagnetic interaction would you accept as an observation?
Okay, so I'm not saying that the like there is something going on with gravity that is, if you use the previous models, it doesn't make any sense. So there is a problem there, right? It has to do with the rotation rates of galaxies and stuff, especially for dark matter. I'm not saying that isn't happening. I'm not saying that you can't see like lensing effects and stuff. What I'm saying is the proposed substance that it is a supernatural, exotic form of matter that cannot be observed in the laboratory as an actual particle physics. There's not a particle physics theory of dark matter and dark energy. It is imaginary.
It's not supernatural.
And it contradicts the standard model of particle physics.
Well, hold on. I just got to pump the brakes on that, because you're saying that there's no model. It's like there's weakly interacting massive particles, the WIMP model of dark matter. It's just like these things are not theories. They're like hypothetical. But you're out here claiming that there's not even a hypothetical model.
I'm saying there's not a particle model of non-baryonic matter, as far as I
I
understand.
literally just named one, though. The weakly interacting massive particle, WIMP theory. I just named one. I don't know if I would say WIMP theory, but like WIMPs. This is like, we do have math that describes what these particles would act like, and they are a major candidate for what dark matter could be.
Okay. So that's okay. So, all right, fine. That's not really exactly what I'm saying. I'm saying that the way that we have a theory of standard model of particle physics, right? We do not have an equivalent model. Like WIMPs is a hypothesis of what this type of dark matter might be like. It's not a model of particle physics. Like this has not been thought out through enough to where they have a particle model for this. And not only that, but it contradicts the current standard model of particle physics.
Okay, so
in order to have non-baryonic matter in this exotic matter, it has to be a completely new type of matter that follows a different type of physics. It's not known to be possible.
Okay, so following your logic here, because we do not have a particle physics model describing gravity, therefore gravity does not exist.
No, we can observe gravitation.
Well, we didn't for
we don't
for
observe
it was a long time
matter.
before we observed gravitational waves, but gravity still existed.
Yeah, but we don't have any particle theory or model of gravity, right? So that is what the point that you've been making this whole time is that that's somehow a defeater for like dark matter or dark energy if we don't have a particle like model for them. But it's literally the same argument that applies to gravity.
Well, there is a particle model. There is a particle model for gravity, though.
Well, we didn't have a model, or we didn't have any observations of the Higgs boson for a long time, but they finally found it after the guy had predicted it, I think like 60 years ago, and now it's part of the standard model.
Right.
So, which is still incomplete, and we don't have a theory of everything. So, physics is still incomplete, and there's discoveries yet to be made, but that doesn't invalidate these fields. You know, it's okay to not know everything.
So you guys believe that 92%, is that what you said, Grayson? 92% of the universe is this exotic matter and exotic energy that was made up in the 80s?
From our current observations, yeah, it does seem like the majority, like I think it is somewhere in the 90% range.
Yeah, it's like more
maybe 92%. I don't remember, but it's in the 90% range based on our current observations of the universe.
Okay. And you guys don't see any issue with that?
I'm tempted to get Leo in here.
But what issue do you see with that? I'm curious.
Oh, well, their model was wrong and it was falsified, so they made up a new one that requires inventing 92% of the universe with made-up fictional stuff that defies the laws of physics. That's sort of a problem to me. I don't know, it's sort of a deal breaker for me. But
what laws of physics does it defy? And also, I would just ask, like, why do you think that we as humans should be able to directly observe every aspect of the universe?
They didn't say that we should.
Well, you said, like, don't you see how it's problematic if 92% of the energy of the universe, like, we haven't, like, directly observed, or we can't, hold in the palm of our hands or something? I'm like, why would we assume that the matter that we interact with on a day-to-day basis is 100% of the universe? I see no logical reason to make that assumption.
Neither do theists. I mean, you guys sound like creationists to me. You guys believe in creation. You believe that most of the universe is supernatural, exotic matter. You guys are creationists.
Nope. None of that is supernatural, and none of that is creationism.
Big Bang is creationism. You guys believe in creation. Like how many billion years ago? 13.
I don't believe in it, though. It's just I agree with the consensus of cosmologists who are a lot smarter than me.
What's your favorite quote from Carl Sagan? In order to make an apple pie from scratch, you must first invent the universe, right?
You're fucked now, Adam. I'm just kidding. Just kidding.
All right. So, well, we talked about talking about CMB temperatures. You guys want to talk about every aspect of this, and now you want to bring in the next guy. Okay, who's the next guy?
Well, I don't know if Grayson, if he has, I know he has limited time, so just to keep the discussion going in case he has to leave, figured I'd add Mr. Leo Phyllis. So how are you doing, Leo?
I'm doing good. I'm just interested in what laws of physics the concepts of dark matter or dark energy defy.
All of them.
Which ones? Let's start somewhere. Name one.
It's pick any one and it defines.
No, yeah, that's what I'm asking you to do. Name one.
It's not. It doesn't exist. Like stuff has to exist.
No, name at least one law of physics that is violated or defied by either dark matter or dark energy.
All right, let's.
Yeah, I didn't think so.
I hate this guy, by the way, Age. I don't know why you're bringing this guy.
How dare you? I mean,
well, to be fair,
I would hate him
asked
too.
The same question that Leo did earlier, but I mean, the only response I just heard was that they have to exist. But like,
you guys have never heard of that before? That dark energy and dark matter defies the laws of physics? Is that a new piece of information to you?
But they're just placeholder terms for phenomena that we don't really know of yet. I don't see how they can be like disproving or contradicting anything. Like they're just like placeholder terms.
And they also don't violate any known laws of physics.
Well, okay. Well, so I was prepared to talk about CMB temperatures. If you want, I can go and provide some evidence and some information on why I believe that. I mean, I've read a lot about it. I don't really believe in that stuff that you guys believe in, so I don't get that deep into like what exotic matter even is, because I don't believe in it.
Why not?
I mean,
why don't I believe in it? It's
do you have any evidence that exotic matter, non-baryonic matter is impossible or breaks the laws of physics? Or like, why do you not believe in it? What's your reason?
Right. So you can ask me that about every single thing we talk about. But
you should have a reason to believe the things you believe, right? I mean, you should have rationales.
Yeah. I do.
Why don't you find it convincing that it's true, I guess? Like,
but
why?
We're not okay. So are we here? Like, just change it to grilling me about my personal beliefs. Then, like, we're here to talk about the cosmic microwave background radiation.
Well, I mean, the discussion has gone to dark matter because you started talking about that, and nobody's stopping you from talking about what you want to talk about. If you want to, and we're talking about the TV earlier. So.
Talk shit and bring in a fifth person, have him talk shit, and then just we're gonna have a lot of just us versus them mentality of.
Wait, I talked shit. Did I talk shit? I thought I just asked you a question and then you didn't answer it, even though you made the claim. That's how I recall that going down.
Well, you talk shit to me in the past.
I don't really care about the past. This is now.
Well, we're talking about the past. We're talking about the Big Bang Theory and predictions of the Big Bang Theory from the past.
I mean, I think we've been fairly cordial. I mean, nobody's
Leo has not
attacking you.
Is what I'm saying.
Well, he's a dick. That's why. I mean, he gets very passionate about science because I think he gets offended when people say that science or cosmology or different fields of science aren't true, and they don't really have a good reason for why they doubt it or disagree with it.
Oh, I gave a lot of really good reasons. And I'm not saying that cosmology isn't true. I'm saying that the creationist version that you guys believe in is not true.
I don't believe the universe was created. I don't even think that's a coherent concept. So I don't know how I could be a creationist in any meaning of the word.
Well, I'm not talking to Leo.
The overwhelming the overarching majority theory in cosmology right now that's accepted is Big Bang cosmology. That's what the astrophysicists and cosmologists agree on. That's the scientific consensus. So,
right, that doesn't prove anything, though.
I'm not saying that it does. I'm just saying that people who are educated, a lot more educated than me in these fields, the fact that most of them agree on this, I find that convincing to where I'm going to defer to them and say these people probably know what they're talking about. So it's more likely that they're going to be right than that it's all bullshit and made up.
Or at the very least, it would require strong evidence to the contrary to disprove that. And so far, I haven't heard any of that. I mean, again, I just want to iterate. In the 20s and 30s, so this is after a lot of the observations that you're talking about, and like the The majority opinion was your opinion, the static state universe. But when the preponderance of statics, whatever you want to call it, the universe being static.
Steady.
But since then, right, the consensus has changed in light of the evidence that has come out since that point in time, which I don't know why you don't want to discuss anything after the 1920s.
Oh, well, that was the topic that I had agreed to with AJ is why I'm frustrated because I wanted to talk about those specific temperatures. But when you guys keep, like, if I point out a problem with something with the foundations, you'll skip ahead to the 80s and then you'll skip ahead to recent stuff and you'll skip back and forth, but you'll treat it as if it's all the same thing.
Well,
so it's not the same thing. It's been the earlier models have been falsified.
Let's talk about the temperatures then. Let's talk about the C and B temperatures.
Okay, let's actually like go through them. Like, let's look at what the temperature predictions were and which ones were right and which ones were wrong. That's what I told you I wanted to talk to you about.
Okay,
and I told you I wanted to have a conversation. I don't want Leo to be here. I really don't like him. Like, he was not just.
It is my channel. So
he was like very aggressive and hostile. Like, he's not a good person.
Well, that's a bit rude. Okay, well, tell me what you want to say about the temperatures.
All right, so you guys believe that the Big Bang theory is one of the three main things that people use as evidence for the Big Bang theory is the redshift evidence, the CMB temperature prediction evidence, and usually like nucleosynthesis evidence, which all of those things have problems. But the temperatures predicted by Big Bang models came after background predictions were already made in the 1800s, right? It was already known that there's a background temperature, and it was already predicted to be 2.7, 2.8 before the Big Bang theory. The Big Bang theorists predict something significantly hotter than that, ranging from 5 Kelvin all the way to like 100 Kelvin. And their whole point in that famous paper, the 5 Kelvin that a lot of people like to quote, is that they're predicting that it's going to be higher than what the other people said. So when you say, oh, well, 5 is close, you miss the point. 5 isn't very close in terms of predicting levels of energy. But it's not close because what they predicted was that it was going to be higher than the background temperature without the Big Bang theory. Does that make sense? Like, I think it's so contrary to your belief and so new that you're not following what I'm even saying.
When in the 1800s did you say they predicted the CMB temperatures? Did you say 1840s?
That prediction was made about the temperatures of the stars, and the guys, he was not talking about temperature on a cosmological scale. And he himself said that there wasn't going to be a very significant prediction. Like, and I mean,
all right,
it's
so you're talking
a different
about
category.
Gualame or whatever the guy's name is?
Yeah, I see. It's hard to pronounce.
Okay, so there's a guy. Okay, so what are you looking at? Wikipedia?
I was looking at that earlier. Also, 5 is 5 a significantly bigger number than 2.7? Because I don't really think that it is. I mean,
not in Kelvin. It's not.
Right.
It is for energy, because energy, like if you convert temperature to energy, you do it to the 4th power. So it's quite a bit more energy that is predicted.
Not compared to each other when you convert both the terms into energy.
Yeah, if you're using one metric, which is Kelvin, then it is close, and it was a close prediction.
But that isn't the prediction. It's 5 and 28 and 20, and then they change it to 30. Like, the one guy in 1 year, he put out like 3 completely different numbers. And the theory, if the theory can predict anything from 5 Kelvin all the way to 150 Kelvin, and they keep changing it over and over again, multiple times a year over decades and decades, that isn't a very specific prediction. They made all of these predictions, and the best you can say is, well, the 5 Kelvin one was kind of close. Like, the people that didn't believe in a Big Bang theory knew the temperature before that.
How could they have? If they didn't think there was a Big Bang, they wouldn't have thought that there would be a relic radiation left over from this hot, dense state. They wouldn't have been capable of predicting a temperature for an entity they would have suspected did not exist. What you said just makes no sense.
It makes no sense to you because you assume that the background temperature has to be a relic. So you're just
no, I don't really care what the temperature is or what it was predicted. The fact that the CMB exists at all effectively proves that the Big Bang happened. So
okay,
no, it doesn't, because it was known about before the Big. It was known about decades before the Big Bang.
No, it wasn't.
I mean, you're just
it was known by
no, like, but it actually wasn't, because prior to the 1920s.
Hold on, Leah. All the people that Adam has brought up who quote unquote predicted this were not predicting any kind of cosmic microwave background. In their own words, they were predicting either like the background temperature of stars or of like interstellar molecules. Like none of these were any kind of intrinsic background temperature of the universe. All of these scientists that are, as you were talking about, from the 1800s or the early 1900s, they all attributed it to them to something other than the CMB.
No, it is the CMB. You guys
why
are.
Why would people who believe in the steady state predict that there would be background radiation?
Oh my God, are you being serious right now when you say steady state?
No, why would people who thought the universe was static predict that there would be
steady state doesn't say that the universe was static. Steady state is an expanding model. Steady state.
You know what he meant, Adam. You know what he meant. He meant static.
I know, but you guys are showing your ignorance by keep saying steady state when that's a creation model like you guys believe in. You guys are the creationists.
Okay. Can I ask you about because I will acknowledge the fact that in the 60s, when the CMB was observed, right, that there was a level of controversy between, and yes, it was the steady state people at the time, but also the static people. There was controversy surrounding the topic about what you're saying. But ultimately, that controversy was dismissed and the consensus was formed because the CMB was measured to follow a black body curve, which is not accountable in any of the static models. That's the main point.
No, but that's just not true that the black body is not accountable in static models, because black body just is a natural occurrence from all this stuff. Like the fact that it's microwave, the fact that it's a black body is just a consequence of the temperature.
So then why was the black body spectrum that was observed, why was that piece of information sufficient to convince the entire scientific community and create the consensus that the CMB was a remnant from the Big Bang? I mean, that's the history of how it occurred. The people that once believed in the steady state and the static universes changed their mind because of the black body curve of the observed CMB radiation.
Right. So you already asked this before, but I'll go back through it. One, it doesn't convince everyone. There's still people that believe in a steady state and a quasi steady state and stuff. It's much more in the minority, but some people still believe that. Some like important scientists. It changed a lot of minds because of what Penzias and Wilson did. It was seen as a confirmation of the Big Bang theory at first.
That's because that's what it is.
Yeah, that's what it was.
Well, that's what it was seen as. But then they found
that's what it is.
Problem. They found the horizon problem,
which has been solved.
The 60s.
The horizon problem has been solved.
But that's a new theory.
Yeah, but you're the one bringing it up. So you're bringing it up to act like there's all these problems. Yeah, but they've been solved. It doesn't matter that they've been solved by new theories. They've been solved.
Just let me respond to what Grayson was saying. Grayson, you're asking, why did it convince so many people? At first, it was convincing, but then they started to see the issues with it. And by the 80s, these major problems of like the horizon problem stuff were recognized, which is why it's now an inflationary cosmology. Like they had to change a lot of it.
But that's not a response to what I was asking specifically about the black body curve. Like that hasn't changed at all. Like that's still observable and it's unaccountable in a static universe model. There's like you say that it's not. You say that that's not true, but I have yet to hear a single static universe model that can account for that observation.
I already responded to what I just responded to this. You're saying that this is, you guys keep doing this. Anytime there's CMB, you count it as a point for its only Big Bang. You see a black body, you count it only as evidence for a Big Bang. There's a black body curve in any of this stuff. Any of these models have black body curves. Like anyone that made a temperature prediction, that temperature itself can indicate whether it's microwave radiation. It can indicate whether it has a black body curve. Like just the basic like laws of thermodynamics define like a thermal equilibrium that's a black body curve, right? And it's like once you have a environment that interacts enough, it goes to a certain temperature and it has a black body. Like it's something that's not unique to any one theory. Black body and microwave and background temperature, that is in all cosmology. Every model has that.
So wait, but what isothermal, opaque, and non-reflecting object in your model emitted what is now observed as the cosmic microwave background?
Grayson, does that address your question?
No, not really. I don't think that you're really understanding like black body radiation, or like the fact that if you could go back in time before the observation and talk to any of these physicists that were proponents of a static or steady state model, like they would not have black body radiation in a background temperature. Like that would not be a part of their model. It would not form a black body curve. Like that is absolutely not a part of any of those models. And I think that you are kind of, I think that you're saying things that you haven't looked into. I don't think that you've looked into the black body curve of the CMB before, to be quite frank.
Well, the thing is, Grayson, it's fine if he wants to claim that there's things in his model that can release a radiation with a black body spectrum. That's why I asked my question that you'll notice he ignored. So in your model, what isothermal, opaque, and non-reflecting object emitted what we now measure as the CMB?
I already asked him where he thinks that the CMB comes from, and he says it doesn't even matter. Like he doesn't have a model or an explanation for where it's coming from. He just thinks that it disproves the Big Bang. Am I getting that right, Adam?
I'm saying in the top. Well, you guys have completely changed what this conversation is. So in the subject,
you wanted to talk about the CMB. We're asking you about the CMB
in the context of the discussion of finding issues with the Big Bang theory and focusing on CMB temperatures. Yeah, what an alternative model doesn't. It doesn't matter if we figure out an alternative model if there's something wrong with the existing model. That's what we're talking about.
I like how you're accusing us of being creationists, but you sound exactly like people who say that we need to teach the weaknesses of evolution. That's what creationists say. And that's exactly what you sound like.
To teach the weaknesses of evolution.
Yeah, which there are none. And you're talking about all of the problems with the Big Bang theory. I mean,
and there just aren't.
There really aren't any, or if they have been, they have been solved
by inventing new exotic matter.
No, by the fact that there's overwhelming evidence that it happened, because we can literally see backwards in time when we use telescopes, because we're seeing light from the past. We can learn a lot just from looking out into space, and we can see the remnants of the Big Bang, which is the leftover radiation, which basically proves that it happened.
Can I post a paper?
Sure.
Or are you guys trying to finish up here? This is why I wanted to exchange notes beforehand, because we don't have time to go through a link right now if Grayson said he has to hurry up and go.
Well, you guys can continue the conversation without me, but
yeah, that's why I brought Leo in here.
Right, because
he's like a pit bull, I keep him on a leash, I'm just kidding.
He's a pit lion.
Yeah.
So you guys want to continue, or are you done, or what?
Well, I thought you were going to put something in the private chat.
Yeah, continue.
Oh, okay. All right, so this is actually shit. I have a PDF of this download. I'll post the title real quick, and I'll find a link to the paper. But this explains what I was talking about.
Yeah, I think you're a contrarian, Adam. I think that is why you don't think that these things are true. I think that you're disagreeing for the sake of disagreeing.
I don't want to be here disagreeing like this. Like, I don't like that. Like, you guys have channels devoted to posturing and these debates, and like, I don't really enjoy that type of conversation. So, I mean, you think it's cool to have like Leo come in and just like yell and shout, and
Leo's barely said anything.
Hit that monetize button beforehand and stuff. It's like, I don't really, I told you ahead of time multiple times before we had this conversation. This is not the type of conversation I want to have.
You're goddamn right. I'm going to monetize my videos. Why wouldn't I?
Yeah. So anyways, that's the name of the paper.
I'm going to monetize the shit out of them, Adam.
This paper is from January of 1995. I also can't find any corroborating work on what they did, so that doesn't look good.
Leo, stop yelling. Okay, you're being extremely rude and vicious, and you're just yelling.
Like if you guys want to have a real conversation, we can.
You keep saying that. Like no one's stopping you from saying the things that you want to say.
Well, anytime I speak, you guys start shouting at me.
No, I'm not shouting.
Okay.
Like you get so defensive this whole time. Like,
because you brought Leo in here. I do not like Leo, and I have a negative history with him. I do not like his attitude.
We've had one other exchange, and it actually didn't end that bad. So I don't really know what Adam's talking about.
Out. I challenged you to have this discussion, and I asked AJ in the same question, would you want to have this discussion? You pussied out and wouldn't have it, and AJ would. I don't know if you remembered that.
Yeah, that was on, I believe it was Amy Newman's. Or was that Mark Reed's channel, maybe? It's one of two. But anyway, AJ, is there something I could explain quickly just for the audience? I mean, I suspect most of them probably know this, but...
Oh, it's from 1992, so don't look at it. Like, that's mentally retarded, but okay.
Well, you didn't post a link in the chat.
Just copy that and look it up.
Oh, okay. Yeah, go ahead, Leo.
So I wanted to explain exactly why the CMB is just effective proof that the Big Bang happened, and it relates to recombination. And this is also how we know why. This is also what explains why the universe has an abundance still of light elements. The universe is still roughly 70% hydrogen in terms of its baryonic mass energy density. So the reason for these two observations and the reason why they're expected if the Big Bang really did happen is because the Big Bang posits that very, very early in the universe's history, obviously the universe would have been significantly denser and thereby significantly hotter than it is today. In fact, there would have been a period where it would have been so hot that light would not have been capable of actually traveling. It would have been consistently scattered off of primarily the electrons and some of the protons that existed in the plasma, the opaque plasma that would have filled space-time in the very, very early stages of the universe. However, as the universe expands, it's going to slowly cool, and things are going to, they're going to dissipate a little bit. Energy is going to start to drop. Well, at some point, the energy is going to drop to the extent that stable neutral atoms will be capable of forming. The electrons and the protons will be capable of binding together to form stable neutral atoms. And when this event occurs, not only will the most of the atoms that are formed be in the lightest elements, which we observe with like 75% helium or 75% hydrogen and 24% helium in the very early universe. And like I said, the universe is still roughly 70% hydrogen. But at the same time, all of that electromagnetic radiation, now that stable neutral atoms have formed, is no longer being scattered by all of the electrons. It's now capable of free streaming, as it's called, through the vacuum of space. So if it is in fact true that the universe very, very early in its history was in a very, very hot and very, very dense state, we should see a high abundance of very light elements, and we do, and we should see at this point in time what would be very low energy microwave electromagnetic radiation that is nearly uniform and homogeneous regardless of where we look or how far out we look. And that's exactly what we see in the cosmic microwave background. Both of these confirming that the period of recombination occurred, both of them confirming definitively that it is indeed true that very, very early in its history, the universe was indeed in a very hot and very dense state from which it evolved, which is the hot Big Bang model.
All right, so are we responding to the group? Am I responding to what Leo just said, or am I responding to Grayson? Grayson, do you agree with AJ?
You can respond to what Leo just said.
Do you guys both agree with what Leo said? Like, you think that the nucleosynthesis and the abundance of the light elements.
Yeah, we agree with what Leo said.
Yeah.
You agree that that's evidence for the Big Bang?
This is the third time I've said yes. We agree with what Leo said.
Okay, but I'm saying specifically the because he didn't say specifically. I don't remember. I actually walked away because I can't fucking stand Leo. But the helium and lithium and deuterium abundance, you guys are all three citing as evidence in favor of the Big Bang that it was a correct prediction.
Yeah. So
one of many.
If the universe has always existed, then why would there be so much hydrogen? Like, what is creating all of the hydrogen in the universe? Like, wouldn't it all have been fused together in stars already?
Wait, do you want me to respond to Leo or do you want me to respond to that?
Go ahead and respond to Leo.
Okay. So and we can get into this. This is why I wanted to focus on one thing, because we can talk about helium abundance. We can talk about lithium abundance and deuterium. The only thing that the Big Bang Theory predicted accurately is deuterium. There's something called the lithium problem, focusing on the fact that the lithium levels that were predicted at first seem right, but as they're making more and more precise measurements, the helium is wrong, the lithium is wrong, and the deuterium is wrong. I'm pretty sure those are the only, I mean, and the height. So you have hydrogen, helium, deuterium, and lithium are the four that they predict. Hydrogen is just the simple, like hydrogen isn't very specific. It's just it's like basically primordial helium is the assumption. So the three specific predictions that they're making is helium, lithium, and deuterium, which is a form of hydrogen, correct?
Yes, it's an isotope.
Okay. So out of those three, it's only deuterium that is correct. So that's not evidence in favor of the Big Bang Theory. It's evidence falsifying that prediction of the Big Bang Theory, and you need to update the model again.
Well, it doesn't really falsify the model. What it shows is that we weren't exactly correct with our predictions about how much lithium would be formed. But anyway, would you be capable of telling me at least two proposed solutions to that problem? I'm just interested in actually how much you've read into this.
To which problem? The lithium problem?
But there are proposed solutions to the lithium problem. I mean, there are other explanations for the amount of lithium that don't involve throwing away the entire Big Bang model.
No, that's what I'm saying is, okay, so you're counting these predictions as correct and patting yourself on the back, but then when I point out, well, actually, three of those predictions are wrong.
Well, are you aware of any of the explanations for the amount of lithium? Are you aware of any of them?
Are you saying from a Big Bang theorist standpoint or from an alternative model?
From Big Bang.
Lord. There's actually two different ways, at least two different ways. I mean, a lot of cosmologists would say that it could be just that the Big Bang nucleosynthesis predictions were somewhat incorrect, or it could be that standard model predictions, like standard model of particle physics predictions, could potentially be incorrect. I don't really know what the scoop is on which direction cosmologists might lean. There are also some solutions that like exist beyond the standard model. People think that like dark matter decay, I think somebody said something in supersymmetry is one way. But I don't know. Supersymmetry is probably wrong, so that doesn't, I don't think. But if I had a guess, I'd probably say it's probably some sort of like standard model predictions that are incorrect.
Okay.
With respect to just how accurate and precise our predictions, or that Big Bang nucleosynthesis specifically is more complete than the standard model of particle physics. And there could be a variety of errors in, like there could be I don't even know where to start. There's like 3 or 4, I think, different problems in certain nuclear processes that we could have over or under corrected for certain processes that could have produced it. There could be processes maybe we're not fully aware of that could have produced it. I think there could be errors in cross-sectional analyses in the particle fit. Like there are solutions to this problem, but the problem isn't the problem for like Big Bang cosmology in general. It just means that some of the predictions were a little bit skewed. That happens all the time in science.
I agree that it doesn't mean you have to throw out the entire thing, but they do keep doing that where they have to do an updated version of the model. So
that's how science works.
So Grayson, to respond to your question, you asked me how would you even have hydrogen in a static model?
Well, I just want to point out that like explanation, like if you have a prediction that doesn't come that isn't like within the observation, like you have to come up with explanations for what like what went wrong in the prediction and what accounts for the observable evidence. And there, I mean, I think that you just acknowledge, and you would acknowledge, that there are numerous such explanations within the lambda CDM model, or like that are independent of like throwing away the Big Bang. I mean, there are lots of explanations for why these could be the case. And I haven't heard a case for like the logic behind this being a justification for disproving the Big Bang.
Also, the fact that there are so many correct confirmed predictions of Big Bang cosmology, that just means that if there is an error in the measurements of deuterium or lithium, the lithium problem, then that makes it much less of a problem because there are so many confirmed predictions.
What are some of the things that you see as confirmed predictions? Because the stuff that Leo brought up that you guys claimed you agreed with, where at this point it sounds like you're saying you agree that there are some issues with it and errors, and they are not correct predictions, but it might have to do with this. You know, it needs some adjusting. We need to adjust to this new data that does not fit with. There was a period where it seemed to match up pretty well. I can't remember the exact times on it because I was just watching a video about this where there was like, I think it was maybe through the 90s, and there was like by the early 2000s, they're starting to get more precise measurements.
So I just wanted to respond to your question about confirmed predictions. So we have the distribution of galaxies, clusters of galaxies on various scales. We have the shape and the chemical composition of distant galaxies. We have something called standard candles, and the relationship between the luminosity and the distance of standard candles, and ratios of isotopes, early isotopes, like we were talking about the light elements of hydrogen and helium, the ratios of those early light elements that were formed at the very start of the Big Bang, in contrast to heavier elements that were formed in the cores of stars. So there are lots of confirmed predictions of the Big Bang. So if we have a problem with the calculations of lithium and it doesn't match the predictions, well, that's one error maybe, but that's not a big deal because we have all these other things that have been confirmed, so it doesn't really matter.
Okay, so the abundance of the light elements, as we established, you guys agree that there's problems with it. So that's not an example of other stuff that it does well. You cited galaxy clusters as evidence for the Big Bang Theory. Explain to me how galaxies clustering is evidence for a model that claims that galaxies are spreading apart.
Because it's homogeneous on large scales.
Okay, so the cosmological principle, which was before the Big Bang, right?
No, this is not the cosmological principle. This is observations of the homogeneity of the universe at large cosmic scales.
Right, but that's
it's the distribution of galaxies. That's the confirming factor. It's not just the fact that there are clusters of galaxies. It's also the distribution of galaxies and the distribution of galaxy clusters.
The interesting thing about it is that the distribution of galaxies largely follows the pattern remnant from the acoustic oscillations moving through the hot plasma of the very early universe, that would have been sort of quote unquote frozen when as density perturbations in the matter distribution during the period of recombination. And those were known as baryon acoustic oscillations, providing further evidence that very early in the universe's history, it was in a very, very hot, very, very dense state from which it evolved, which again is exactly what the hot Big Bang model states.
Yeah, the patterns in the cosmic microwave background predict the patterns of galactic clusters.
Okay, so AJ, I'm not understanding how you see galaxy clusters as, and you have to take into consideration superclusters and these huge structures that seem to contradict the age of 14 billion years.
They don't. I just explained that, like the patterns in the CMB reflect the patterns we see in galactic clusters. I mean, do you acknowledge that?
No, I've already said that. I see even the fact that there's not just superclusters in these larger structures, but the fact that galaxies cluster together alone contradicts the idea that galaxies don't cluster together, they spread apart. They're completely opposite claims.
No. Gravity. Like if things are far away, the gravity force between them is going to be weaker. They're going to expand with the expansion of space and time farther apart. But if they're closer together, the force of gravity is stronger by the inverse square law, and they will cluster together. I mean, it seems very straightforward and easy to understand to me.
So at what point do they stop structuring? Because we have clusters, we have superclusters, we have these complexes.
Based on the fault, like the inverse square law of gravity. If things are too far away, they're obviously not going to cluster because the force of gravity between them is going to be too weak. I mean, that makes sense.
It weakens exponentially as you get farther away.
I don't see how you're explaining something with that, though, because what I'm saying is if you're claiming that galaxies are spreading apart or have the appearance of spreading apart because the space is spreading apart, at what stage are the galaxies spreading apart? Because we see them clustering together.
Here's an excellent illustration of this, right? Every single galaxy that we see, like, is expanding away from the Milky Way, except for one, right? The one that's the very closest to us. And why is that? Because it's close enough to where its gravity is causing it to come together with the Milky Way, the Andromeda Galaxy. That's an exact illustration of what we're talking about here. If they're close enough together, the force of gravity is going to overcome the expansion.
Wait. Just to make sure I'm understanding, are you claiming that Andromeda is the only blue outlier we've observed?
Yes. It's the only galaxy that's getting closer to us.
You're saying you're interpreting a blue shift as velocity, and you're saying that Andromeda is the only blue outlier?
It's not velocity, it's parent velocity. There is a difference.
Right.
Okay, so yeah, the Andromeda Galaxy is the only galaxy that's getting closer to us. All the rest are expanding farther away.
That's not what I'm asking you.
It is what I'm getting. Answers what you're asking me. Yes.
Okay, so interesting. Because I know of other ones, but I don't have all this stuff right in front of me. I'd have to go through it. There's other. So if you look into blue outliers, you guys are familiar with that term?
I've never heard it before. You just mean something that's blue shifted?
Yeah, blue outliers it's considered an outlier because it's outside of the very strong trend of things being redshifted, but there are things that are pretty far out there that are still blue shifted, and it's sort of this interesting anomaly. But it's not just Andromeda that has a blue shift. There's these interesting cases. That's why I'm saying, Grayson, that's why before we got in here, I was saying it's not really, they call it the Hubble law. It's a very, very strong tendency, but it's not like a law in the sense that it has to be that way. There's a lot of like the majority of what we observe is red shifted, but not everything. There's stuff out there that's blue shifted. So if it really is from expansion, why is there stuff that's blue shifted?
Are there any other galaxies though that are blue shifted?
I think largely you see quasars,
but not galaxies besides Andromeda.
I would have to. I have to look it up. I don't remember everything off the top of my head.
Well,
we can look up blue outliers, and I'm interested. How can there even be a blue outlier if there's expansion?
Because they're from quasars. They're getting ejected from black holes.
And yeah, this other galaxy is close enough to us that gravity is counteracting the expansion because we're close enough together.
Okay.
On that scale.
Also,
the universe is expanding.
I just want to make the point real quick that the blue shift is relative to the rest of the galaxy that the quasar is in, right? So it's not like it's blue shifted as it's coming towards us. It's just less red shifted than the rest of the host galaxy of the quasar. So this is all explainable within our current understanding of physics, and it makes sense. It's not like a weird this quasar is coming towards us, but the rest of the galaxy around it is going away from us.
Okay, so but Grayson, if you would agree though, then so maybe it is largely quasars. I haven't looked into blue outliers recently.
Yeah, it is quasars.
If there were galaxies that had a significant blue shift that were interpreted as being very distant, that would be a good question. Like, how the fuck can it do that if the universe is expanding?
Yeah, which is why we don't see
the blue shift is, again, like Grayson said, is with respect to their rest frame. So that's like they're blue shifted with respect to if they were stationary, given by the things around them, not us. So there's still a redshift from them to us as a result of the expansion of space.
And so if redshift is from the expansion itself, why isn't it an exact perfect relation corresponding to the expansion? Why is it like this range that the close ones are a little bit red shifted, the further ones, but it's like a range. It's not just an exact.
Because the expansion of space is a metric expansion of its scale, measured over sufficient distances, which means that the larger the distance between two objects, the greater the redshift between them, which means the further an object is from us, the greater the redshift that it's going to give off.
But what I'm saying
That
is
we're going to measure, I should say.
Right, but what I'm saying is, if you see these charts, right, it's not like there's a line and all the galaxies are just on that line. The ones that are lower on the line, it's like, you know, there's a variation to how redshifted they are.
Yes,
And
because
there's quite a
they
bit of
appear.
variation.
Yeah, because
as
they
the
appear at
expansion rate
different
is increasing.
distances.
Yeah, Adam, do you think that there is any margin of
Hold on.
error in our estimation of distances of these objects?
Hold on, because maybe you guys aren't thinking of the same type of diagram I'm talking about. If you look at
Well, you're talking about a diagram with distance versus like redshift, right?
Yeah, yeah.
And you're just plotting it
You know
on
what I mean.
axis and seeing how linear it is, and you're saying that there's a certain spread, there's a margin of error. And I'm asking you,
No, not a
do
margin
you
of
think
error.
that there's a margin of error. And by margin of error, I mean like a variation from a linear like line describing like a Hubble law prediction. So do you think that
Right.
there's any margin of error in our estimation of these distances?
Oh, I think there's way more than a little bit.
So then wouldn't that explain what you're asking?
But do you guys think there's a huge error in the distances? I'm guessing you don't.
There's a margin of error.
Okay, but you agree. Everyone here agrees that the Hubble law is not an exact, precise thing. It's like there is spread.
No, that's why
it's
most
a law.
cosmologists actually call it the Hubble parameter now, because it isn't really a
Okay.
law. It never has been.
Okay, so why do you guys? So, Grayson, it sounds like you're saying because that's a margin of error. Do you think that there is a variation in the redshift distance correlation, or is it a margin of error? In other words, is there a range, or is it
The range
appears to be a
is
range
coming
because
from
there's a
our margin of error of estimating these distances, right? Like these distances are estimations based on like the cosmological ladder. Like they're not going to be precise. They're going to come with a certain range of potential distances with the confidence interval, and it's that margin of error in the estimation of the distances that is producing the effect that you're describing.
So you think it's just a margin of error?
I've been very clear about that.
And I'm just trying to see, because we're talking with three people against one here. AJ, do you agree with that? Leo, do you agree with that?
Wait, I'm sorry. What? Agree with what?
The variation, it's not you said it's the Hubble. What did you say?
Hubble parameter?
I'll explain, but because he's saying that if you plot like a distance versus a redshift, and like Hubble's law would predict like a straight, you know, y equals x kind of a line, a slope. And he's saying that when you actually plot the real data, like, yes, like that, you know, you still get like whenever you do like an r squared, you'd still get that slope, but there's like a margin of error where they fall along this line. And I'm saying that a very likely explanation for the fact that these are not perfectly linear when they're plotted is that the distance, the x-axis or distance, y-axis, whatever you want to say, is an estimation of the distance that's going to contain an inherent margin of error in itself.
Right. And do Leo and AJ agree with that? That it's a margin
I
of
don't
error?
know. I would have to see what chart you're looking at before I could comment or speculate about what it says or doesn't say.
Okay.
I mean,
Sure, I agree with Grayson.
It's easy enough to conceptualize a chart, right, demonstrating Hubble's law. You can imagine that, right, Leo?
I'm sorry. I'm also like half reading a paper on blue outliers amongst intermediate redshift quasars.
Okay. Just imagine a chart demonstrating Hubble's law. One axis is distance, one axis is redshift, right? You can imagine that.
Yeah.
AJ, can you
And when you use
something?
real life data, it's not going to form a perfectly linear line, right? There's going to be like some variation in the points.
If you share your screen, I'll add it. But
think so. Like I can't, like, it's hard for me to picture it because that's setting an ideal scenario when he's not looking at an ideal graph. He's looking at an actual graph. I would need to know what it says.
He's asking, why isn't the actual graph the ideal graph? That's the question. And I'm saying
I don't know.
There's a margin of error in estimating the distances.
Like I said, I don't know what he's looking at. I need to see what he's looking at.
You just described what he was looking at. You said the actual graph versus the ideal graph. He's describing the actual graph, and he's asking why is it different than the ideal?
But you could just say yes. I agree with Grayson. So go ahead from that, Adam.
Okay, so if you think it's a margin of error, then that's different, because you don't think that there really is like this range of scatter. You think that it's just because of the error. You don't think that there literally is a slight variation in redshift as it correlates to distance. You think there's an exact linear relationship, but there's a margin of error in how we measure it and not knowing what it is.
Yeah,
yes,
just
that's the
being
same with
arbitrary.
that's the same with every observation in science. There's always going to be a margin of error with measurement.
Yeah, so I think that I'm gonna wrap the stream up in just like a few minutes, if that's okay with you guys, because this is sort of been fun, but I feel like we're sort of going nowhere with this. So yeah, awesome. Oh.
Okay, cool. And Leo, what did you say that they were calling Hubble's law now instead of a law? That was new information to me.
The Hubble parameter, I believe.
Hubble parameter. Interesting. I'm going to look more into that. Thanks.
Mm-hmm.
Alrighty. Well, yeah, thank you guys for joining us, coming on, Grayson, Adam, and Leo, and yeah, I don't know if you guys want to hang out in the offline, but yeah, thank you guys for watching, and peace out.